After we opened the box and sorted through all the items, we decided which items would be most useful for building each device. For the compass, we decided that we'd use the small cup, the water bottle, the needle, the magnet, the masking tape, and the scissors. For the flashlight, we decided that we would use the batteries, the wire, the light bulb, the pliers, the scissors, and the electrical tape. And lastly, for our telegraph, we thought the most useful items would be the nails, the screws, the screwdriver, the batteries, the wire, the wooden board, the metal clips, the metal plates, the pliers, the scissors, and the electrical tape. Okay, we're making the compass. So this is a compass in water. We're using the needle, the magnet, a piece of tape so the needle floats, and the cup and the water.
Yeah. So now you can rub the
We constructed our compass with a cup filled with water, a needle, a piece of tape, and a magnet. We started by using the magnet to align the magnetic domains in the needle. Magnetic domains are small chunks of a magnet that each contain billions of atoms. Each magnetic domain has a direction that is determined by the arrangement of the atoms inside the domain. If many domains inside a magnet are in random directions, they are likely to cancel each other out, and the magnet is not considered to be magnetized. In a magnetized magnet, the majority of the domains point in the same direction. That direction will be the magnet's north pole. We swipe the magnet along the needle about 30 times to give the needle its north pole. After that, we put a piece of tape on the needle so that it could float in the water. We placed the needle in the water and watched as it turned around to face the direction of north. The magnet faces in the direction of the magnetic north pole, not the geographic north pole. The geographic north pole is exactly pointing at the north tip of the Earth, and is the direction you would find on a map or a globe. Magnetic north is the north that the needle aligns to because it follows the magnetic field lines of the Earth. The reason the lines are different from actual north is because the magnetic field lines of the Earth change slightly over time, which causes them to differ from the actual geographic direction of north. Good. So the compass is in the direction of the magnetic field lines of the Earth. So that's why it's pointing to magnetic north. Magnetic north is slightly different than true north because magnetic field lines on the Earth change over time.
Then we're going to do the flashlight.
Our flashlight consists of 2 D-cell batteries, a small light bulb, a short conducting wire, and some pieces of tape to hold it all together. We stack the 2 batteries on top of one another and put the side of the bulb on top of the positive terminal of the battery. The wire connects the negative terminal of the battery to the bottom conduit of the bulb. It doesn't matter which conduit of the bulb you put the positive or negative terminal of the battery to, because with light bulbs, the ends are interchangeable. When the circuit is closed, there is a potential difference, or a voltage, which is supplied by the battery. It creates a current in the conducting wire which powers the light bulb, making it a functioning flashlight.
Good job, good job. Check it. Oh, we have a light, we have a light. Nice, very nice. Now we need the kind of switch, right? Oh, very nice. Yay! We made it!
Okay, so I'm going to show some calculations for our flashlight. So for our flashlight, we can use Ohm's law, and we can also use power equations to do some calculations. So I'll start with Ohm's law. Ohm's law is voltage equals current times resistance, or there are different rearrangements of the equation. So let's say that for this bulb, flashlight, we were given a 1.5 volt battery, and the bulb requires 3 volts and can have a current of 0.5 amps. So in that case, we would need 2 1.5 volt batteries in order to supply the 3 volt bulb, right? And with these specifications, we can figure out what the resistance of the flashlight would be using the voltage and the current. So we'll use this formula because we want to find out what the resistance is. We have the voltage and we have the current. So plugging in the numbers, we'll plug in our 3 volts for our two 1.5 volt batteries divided by the 0.5 amp bulb. And when we do the calculation, we get a resistance of 6 ohms. So that's the resistance of the bulb in the flashlight. Now we can also do some power equations. Power is measured in watts, and the formula for power is power equals current times voltage. So if we plug in the current and the voltage that we have for this flashlight, multiply them, 0.5 amps times 3 volts, we get a power of 1.5 watts. So the flashlight has a power output of 1.5 watts. The wireless telegraph was one of the first means of long-distance communication ever created. It works by sending out electrical energy which travels through the air and can be received by a transmitter a long distance away. The way it works is as follows. When the switch is closed, there is a complete circuit and electricity flows through the wires. The electromagnet is switched on and it pulls down the metal plate which is touching the nail. It pulls the metal plate down because the electromagnet creates a magnetic field around it which attracts the plate. When it pulls the plate away from the nail it was touching, it breaks the circuit, producing a spark. With the circuit broken, the magnetic field collapses and the metal plate springs back up to touch the nail and makes the circuit again, causing the electromagnet to pull it down again, and so on. It continues to spring up and down quickly and produces sparks. These sparks are radio waves that can be picked up by a radio. When we put the radio near our telegraph, it picks up the radio waves in the air and the interference can be heard on the AM radio. An electromagnet is the main component of a wireless telegraph. An electromagnet is created by wrapping a wire around a nail and connecting the two ends of the wire to a battery. This creates a magnet because a current-carrying wire has a magnetic field around it. If you wrap a wire around a nail hundreds of times, the magnetic field from the wrapped wires all get added to each other, and one very large magnetic field is created around the nail. The benefit of an electromagnet over a regular magnet is that an electromagnet can be switched on and off by opening and closing the circuit in the wire. This allows you to pick up something metal and drop it easily. Or in the case of a telegraph, it allows you to attract a metal plate, which in turn makes a spark that can be used as a form of communication.
So I take a wire and a nail, and I'm gonna turn the wire around the nail a few times, to create an electromagnet. So turn it. So we use 2 batteries, some pieces of metal, 2 nails, 1 mini nail, and this nail we use a wire and we turn it around the nail to create an electromagnet, and this piece of metal right here is the switch of the telegraph. And now Jonathan will show us how it works.
Now we're going to check if the telegraph is working. We're using the radio to check if it's creating any electromagnets pulses, and we can hear a noise every time I push the switch.
So let's see our products. We have the telegraph, very nice telegraph. We have the flashlight right there, look at this. And we have the compass, same way as the compass in the iPhone. And we're done.